Hi, so we're doing part 2 of section 5.2. Now we're going for question 7 to prove by mathematical induction that the sum of the first n powers of 2 is going to be equals to 2 to the n plus 1 minus 1. So once again, since we're proving this by induction, we got to prove the basic step. And so the basic step for this one, of course, we're defining this as P of n. So the basic step will be what happened in 1. And so the left side is just going to be equals to 1, right? Since we have 2 to the 0. Or, yeah, 2 to the 0 here. And the right side would be, this got to be not n bigger than 1, but n bigger than 0 here. And the right side is going to be 2 to the 0 plus 1 minus 1. So that's 2 to the 1 minus 1, and it's going to give me 1. Okay. Notice that if I actually just do 1, 2 to the 1, that's going to give me this 1 plus 2, because 1 is only possible to get with these powers if this is 2 to the 0. So it got to be 2 to the 0, 2 to the 1. And so if you test it with 1, then the left side is just going to be 1 plus 2, and the right side is just going to be 2 to the 2 minus 1, which in both cases is equals to 3. So basic steps going to work out regardless. Now, the induction hypothesis is going to be assist k in the integers, so that 1 plus 2 squared plus 2 to the k is 2 to the k plus 1 minus 1. Now I want to show the k plus 1 step, which is 1 plus 2 squared plus 2 to the k plus 2 to the k plus 1 is equals to 2 to the k plus 2 minus 1. Now let's prove it. We'll start with the left side. 1 plus 2 squared plus 2 to the k plus 2 to the k plus 1. Notice that this piece is just going to be pk. So this is equals to p of k plus 2 to the k plus 1. And now, by hypothesis of induction, then this piece is just going to be 2 to the k plus 1 minus 1. Plus 2 to the k plus 1. Okay. So now, notice that this is twice 2 to the k plus 1 minus 1. But what is twice 2 to the k plus 1? Well, this is going to be 2 to the k plus 1 plus 1, which is 2 to the k plus 2 minus 1. So we just prove what we wanted to show. We'll start from the left side, reach to the right side. And so by principle of mathematical induction, P of n is true for n bigger or equal than 0. Now let's do question 8. And question 8 here is saying, prove by mathematical induction that for all integers bigger than 1, the sum of I equals 1 to n of I times 2 to the I is n minus 1 times 2 to the n plus 1 plus 2. So this one has a complicated formula, but the idea is exactly the same. We want to start with the basic step. So basic step, let's prove P of 1. And of course, this is going to be P of n. This is the original statement. So the left side, P of 1 will be from I equals 1 to 1 of I, right? I 2 to the I, which is just simply 1 times 2 to the 1, which is 2. Now the right side is plugging in n minus 1. So 1 minus 1, 2 to the 2 plus 2. Now 1 minus 1 is 0, so I'm just going to get 2. So here the basic step is good. Now the induction hypothesis, then we have that this is K or to be fair, should not be saying that this is K, should be saying that for K that belongs to the integers, because we want to think of this as all possible K. P of K is true. So that means that the sum from I equals 1 to K, from I 2 to the I, is equals K minus 1, 2 to the K plus 1, plus 2. Now, we want to show P of K plus 1, which is what? The sum of E equals 1 to K plus 1 of E2 times 2 to the I is equals to K 2 to the K plus 2 plus 2. Notice that essentially I'm plugging in K plus 1, so that's why it becomes K, and this becomes K plus 2. Now let's start. Let's prove it. Once again, let's start from the left side. So we have the sum of I equals 1 to K plus 1 of I 2 to the I. And I can see this as the sum up to K plus the term K plus 1. So K plus 1, 2 to the K plus 1. Okay, so this is the by hypothesis of induction. Since this is equals to pk plus k plus 1, 2 to the k plus 1, then that's going to be equals to just k minus 1, 2 to the k plus 1 plus 2 from pk, and then plus k plus 1, 2 to the k plus 1. Now notice that I have common 2 to the k plus 1 from these two terms. So I can factor out 2 to the k plus 1, and I'm going to have k minus 1 plus k plus 1, and then outside plus 2. Then notice minus 1 goes with minus 1, and I get 2k. K plus 2. But this 2 is going to multiply with this, and then it's going to become k 2 to the k plus 2 plus 2, which is exactly what I wanted to show. So by principle of mathematical induction, P of n is true for n bigger or equal than 1. Okay, so that was question 8. So now let's go to question 9. For question 9, we want to prove that for all integers bigger than 4, 2 to the n is less than n factorial. So the basic step, we want to prove p of 4. This is p of n. So p of 4, because n starts at 4 here, bigger or equal than 4. Notice that 2 to the 4, which is 16, is less than 4 factorial, which is 24. So the basic step holds. Now, for k that belongs to the integers, pk is true. And so this is the induction hypothesis. We have that 2 to the k is less than k factorial, right? This is for k bigger than 4, of course. And we want to show p of k plus 1, which will be equivalent to proving that 2 to the k plus 1 is less than k plus 1 factorial. Okay? So now let's prove that. So the way that we're going to do this inequality is we're going to start from one side. So we're going to start here from, so let's show it. 2 to the k plus 1, I can see it as 2 times 2 to the k. But by hypothesis of induction, this is less than 2 times k factorial. Okay? But in general here, 2, because since k is bigger than 4, k plus 1 is going to be bigger than 5, which is bigger than 2. So because of that, then 2 is less than k plus 1 times k factorial, or less than k plus 1 factorial. And so here, I just prove what I wanted to show. So by principle of mathematical induction, p of n is true for n bigger than 4. Now let's continue with question number 10. So question number 10 says, identify the error in this proof. We have for all n bigger than 1, 1 plus 2 up to n is n squared plus n plus 1 divided by 2. Here the proof says, inductive step, assume that 1 plus 2 plus k equals k squared plus k plus 1 divided by 2. Then the sum of 2k plus 1 is just going to be equals to k squared plus k plus 1 divided by 2 plus k plus 1. So what is wrong with this approach? Well, the fundamental problem here is that notice that this is just a piece of induction. It doesn't have the basic step. The basic step is super important to prove all the time, just to know that at least the inequality is functioning for the one value. So this is saying for n bigger than 1. So the left side of this identity is going to be the sum from 1 to n. So it will be the sum from 1 to 1 for p of 1. So the left side will be 1. Now the right side, when plugging in 1, there will be 1 squared plus 1 divided by 2. And this is 3 halves. Notice that the left side is going to be different from the right side. So we do not have the initial basis step. So this is the big problem here. And this just showcases why skipping the initial step can be troublesome. Okay? All right, so now let's jump to one case of inequality that can be a little complicated. We have for which integers n is 2 to the n bigger than n squared. Make a conjecture and prove it by induction. So here, once again, the problem is, well, I don't have an initial step mark, so I need to start checking when this is going to be true. So let's say for n equals 1, we have 2 to the 1 on this side, and then this side is 1. So we can kind of think that this is going to work from n equals 1. Let's test for another value just to be sure. For n equals 2, 2 to the 2, and 2 to the 2 will run into problems because 2 to the 2 is 4. And here, this is also 4. So 4 is not bigger than 4. So we have a problem here. So for n equals 3, 2 to the 3 is 8. But now, this is saying that 8 should be bigger than 3 squared. That's not going to happen because this is 9. So this is not going to work. So notice that it's not working so far. Let's do n equals 4. Well, at this point, we have 2 to the 4 bigger than 4 squared. 2 to the 4 is 16, and 4 squared is actually 16 too. So we don't have it. A number is not bigger than itself, so it's not going to work. Now let's go with n equals 5 and see if it changes. 2 to the 5 is 32, and that's actually going to be bigger than 5 squared, which is 25. So far, seems like after 5, maybe it's going to work out. N equals 6. 2 to the 6 is 64. And 6 squared is 36. So it looks like after 5, we're good. So now we can say that for n bigger than 5, 2 to the n should be bigger than n squared. So we found our basis case. And we already proved that P of 5 was good. So we're going to jump to the hypothesis of induction, which is P of k, which is essentially saying 2 to the k is bigger than k squared. Now we want to show P of k plus 1, which is 2 to the k plus 1 bigger than k plus 1 squared. So this might require a little bit of playing with the inequality. You want to say, okay, so 2k plus 1. So let's write here, let's show it. 2k plus 1 can be seen as 2 times 2 to the k. So notice that because we have 2 to the k here, we can apply the induction hypothesis. By hypothesis of induction, this is bigger than, this 2 remains, and this 2 to the k is bigger than k squared. So we have that this is bigger than 2k squared. Now notice that because we want to reach that this is bigger than k plus 1 squared, so we want to show that 2k squared is bigger than k plus 1 squared. We want to know if this is true. So let's break this down. 2k squared is bigger than k squared plus 2k plus 1. So if we subtract 1k squared, this is essentially saying that k squared is bigger than 2k plus 1. Or that k squared minus 2k minus 1 is bigger than 0. But this is actually going to be true because since k, we can write this as k times k minus 2 minus 1. So we want to show this. But now, k is bigger than 5. So k times k minus 2 is actually going to be bigger than 5 times 3. K is bigger than 5. K minus 2 is bigger than 3 then. And so if we have K times K minus 2, that's going to be bigger than 15. And so minus 1 here, if we put a minus 1 extra in there, K times K minus 2 minus 1, that's going to be bigger than 15 minus 1, 14, which is bigger than 0. So for K bigger than 5, this is true. And so we can come backwards. So we can say here, but as K bigger than 5, then we can kind of say K times K minus 2 minus 1 is bigger than 14, bigger than 0. And so that means that K squared minus 2K minus 1 is bigger than 0. And that is equivalent to saying that, getting back in this direction, that 2K squared is bigger than K plus 1 squared. So since I show with this that 2K plus 1 is going to be bigger than K plus 1 squared, I do what I needed to do to show the K plus 1 step. And now by principle of mathematical induction, then P of n is true for n bigger than 5. All right. Now let's finish with question number 12. So it says, for all integers bigger than 1, 1 cube plus 2 cube up to n cube is going to be given by n times n plus 1 squared divided by 2. So first, let's check the basis case. So basis case, on the left side, we're going to have 1, since this is simply for n bigger than 1. N cube is just going to be 1. And the right side will be 1 times 1 plus 1 over 2 squared, which will be what? 2 over 2, 1, 1 squared, 1. So the basic case holds. Now, for k that belongs to the integers, we assume P of k, the hypothesis of induction, which will be that 1 cube plus 2 cube plus k cube is going to be equals to k times k plus 1 over 2 squared. Now we want to show pk plus 1, which is the first k plus 1 cubes will be equal to k plus 1, k plus 2 over 2, everything is square. So now let's show it. What we do, of course, is we start with the first k plus 1 cube on the left side. And remember that we can see this as the k condition, P of k. And so what this tells me is that I should be able to see it in this way. Now, at this point, I can just factor out some terms here. This is going to be k squared, k plus 1 squared, and over 4. And I can write this as 4k plus 1 cube over 4. If I factor k plus 1 squared, I'm going to get k squared here plus 4k plus 1. And over 4. Now notice that this is k squared plus 4k plus 1. So let me write this out. K squared times k squared plus 4k plus 4 But if you see this, this is just the k plus 2 square binomial. And so essentially with this, we have proven that this is going to be k plus 1 times k plus 2 over 2 everything square. So we just prove the n plus 1 condition. And so this means that P of n is going to be true by n equals or bigger than 1 by principle of mathematical induction. All right, so this covers all the examples of mathematical induction for this section. In the next section, we're going to check some examples in divisibility.